Okay, in this video, derive the exact transmission line losses formula. In the last video, to derive the transmission line losses formula by using the coefficient method, coefficients. But in this method, exact transmission losses formula. So exact formula for calculating transmission losses may by making use of bus powers, and the system parameters. We know that the power equations, apparent power S equal to P plus J into Q, real power, and combination of reactive power. Combination of reactive power. So the exact formula for transmission line losses by making use of the bus powers and system parameters, where let SI is the total injected bus power at bus I and is equal to generated power minus the load at bus I. The summation of all bus powers over all the buses give the total losses of the system. We know that according to load flow equations, here the load flow equations PL plus J into QL. This PL means real power losses, here the reactive power. Total summation of I equal to 1 to N. This is one total apparent power. This is the total apparent power in the load flow equation. The summation of I equal to 1 N. So we know that the formula P equal to V into I. So here VI into II conjugate 2. VI into conjugate 2. So conjugate to V bus transpose T transpose I bus conjugate 2. We know that the voltage equal to V equal to Z into I. Z means impedance. So V bus equal to Z bus into I bus. So V bus in this second equation substitute in the first equation, where the Z bus is the bus impedance matrix of the transmission network, where the Z bus is the bus impedance matrix of the transmission network and is given by Z bus equal to, we know that what is the impedance, the combination of resistance and reactance. So Z bus equal to R bus plus J index bus. So R means resistance R11 and R12 and soon R1N and R21 and R22 and soon R2N and soon Rn1 and Rn2 and Rn. Similarly J complex variable x11 and x12 and x1n x21. Similarly this is the reactance matrix, this is the resistance matrix. From equation 1 and 2 we have PL plus J into QL. After substituting Z bus, so PL plus JQL I bus transpose plus I bus transpose Z bus transpose I bus conjugate 2. So after substituting Z bus equal to, after substituting V bus equal Z bus into I bus, so V transpose means I bus transpose Z bus transpose into I bus conjugate 2. Then I bus transpose into Z bus transpose into I bus conjugate 2. See, in the law, this step can be written because Z bus is the symmetric matrix. Symmetric matrix means Z bus transpose equal to Z bus. Transpose, the matrix is implemented by transpose. Then we will be again for the same Z bus matrix. So this is the because of Z bus transpose equal Z bus equal to. So because of Z bus is the symmetric matrix. So I bus means IP plus J into IQ, IP plus J into IQ. They are written as the matrix form IP1 and IP2 and IP1 and IP2 and soon IPN. Similarly, J into IQ1 by IQ1, I2 and IQN. This is the I-bus matrix in the form of current. I-bus can be written as simply IP plus J into IQ. So the equation can be written as, in the above equation can be written as PL plus J into JQL. In the I bus transpose can be written as IP plus J into IQ transpose. The Z bus is can be written as R plus J into IXS. And the IP by I bus means IP plus J into IQ I bus. The conjugative means IP minus J into IQ. So in this equation, separating the real part PL from the above matrix product, we get PL equal to IP transpose into IP transpose into R into IP, and first those terms are multiplied, then after the final equation is the product of all terms, you get the final equation PL equal to IP transpose R into IP plus IP transpose X into IQ and IQ transpose R into IQ minus IQ transpose X into IP. This is the all terms are cancelled in this equation. So the remaining terms are involved in this equation. The PL means transmission line losses formula. Here X also symmetric matrix. X also symmetric matrix. IP transpose X into IQ equal to IQ transpose X into IP. So those terms are cancelled. The remaining equation PL equal to IP plus transpose into R into IP plus IQ into transpose R into IQ. In above equation can be written as, this expression can be written using index notation. Index notation PL equal to the summation. This is the induction notation. PL equal to the summation of n I equal to 1 to k equal to 1 to n or j k into IPJ, IPK plus IJ into IQ. This is the transmission line losses expressed in terms of bus currents only. So bus currents only. So in the first already told the exact formula calculating the transmission losses by making use of bus powers and system parameters. Now derive the equation. So these transmission losses can be expressed in terms of bus currents. In actual power plant, this is the power loss equation in terms of only bus power. In actual power plant, the system operator usually known the bus power and nodal voltages. Therefore, it is more practical to express PL in terms of those quantities. So the actual power plant, the system operates knows the bus powers and node voltages. This is the system parameters and the power loss expression in terms of bus powers and system parameters. System parameters nothing but voltage and current. In this expression only involved for the bus current, but in actual power plant the total losses, transmission losses can be expressed in terms of system operators usually bus powers and nodal voltages. Therefore, it is more practical to express PL in terms of those quantities. Bus powers at bus I we have, so PI at bus I, the bus powers PI plus J into IQ, VI into IA conjugative. So VI is the same term. The I conjugative, we know that I bus equal to IP plus J into IQ. This is involved for the conjugative, the replaced by the plus, replaced by the minus, replaced by the minus. So VI in this equation can be written as in terms of polar form or rectangular form, VI cos I theta plus J into sin theta, IPG into I. So here, and multiplying both terms and multiplying the finally separating the real and reactive powers, real and imaginary terms can be divided. So pi equal to vi into cos delta I ipa plus vi into ip vi into iqi sin delta I, and qi equal to vi modulus of vi sin delta I ipi minus cos delta I iqi. Those are the separating for the real and reactive power, real and imaginary terms, and equating the above equations, left side compared to the left and right side, and separate the terms in the real power and reactive power generations. So now solving ipi and in this above equations can multiply both sides, and the first in the pi equations cos delta I and qi equation sin delta I, and both sides are multiplied, and finally we got the ipi equation 1 by vi into pi into cos delta I plus qi into sin delta I. Here the delta is the phase angle, and the iqi in the above equations multiply in pi equation sin delta I and qi equations cos delta I, multiply, we get the final equations. The iqi is the value of iqi equal to 1 by modulus of vi pi sin delta I minus qi into cos delta I. This we have expressed here the real and imaginary components of the bus current in terms of bus powers and bus voltages. So in this expression as a real and imaginary components, the bus currents in terms of bus power at the bus power. This is the P and the IQ is the bus powers, and VI is the nodal voltage. Substituting those values in the expression power losses, we get the after some algebraic equations. PL equal to the summation of j equal to 1 to k equal to 1 to n alpha jk pj and pk plus qj and qk plus beta ij jk qj pk minus pj qk. So here the compare the general losses formula, the alpha jk equal to alpha jk by vj vk cos delta I minus delta k. Similarly bjk equal to rjk vk modulus of vk and modulus of vj sin delta j minus delta. This is the exact formula for losses of the transmission network. So the actual power plant exact formula can be represented in the bus powers and system parameters. System parameters nothing but voltages and current, and in terms of bus power means real and reactive power. In the first we got the expression for the power loss formula only in terms of bus currents, but actually in power plant is the bus powers and nodal voltage can be also derived in terms of bus powers and bus voltages. So this is the exact loss formula. Thank you. This is the last topic of the first unit. Thank you.